Hello, my name is Kevin Ang. I'm a sophomore at Milburn High School in Milburn, New Jersey, and my project today is flight performance improvements for the Mars Ingenuity helicopter. Special thanks to my mentor Humberto for helping me work on this project. First, we'll be going over my introduction and goals of my project, then methodology, analysis, limitation solution, and finally conclusion. What is Ingenuity? Now, the Mars helicopter, also known as Ingenuity, which is this picture on the left, is the first autonomous NASA helicopter operated on Mars from 2021 to 2024. It has reached a flight time of 169 seconds and has a mass of 1.8 kilograms and a wingspan of 1.21 meters. And it spins its rotors very fast, around 2,400 RPM. Ingenuity uses the CLF 5065 airfoil, and an airfoil is the shape of the side of the blade of the wing, as shown in this picture on the right. And this will be the main focus of my research, as the goal of my research is to investigate potential improvements to the airfoil by changing its shape, and this will increase Ingenuity's flight performance in flight time, payload, or flight rate. Now, what is an airfoil? An airfoil is the cross-section from the side of the wing, as shown on the last page, and the airfoil shape decides the properties of the wing. So here's some relevant vocabulary terms to airfoils. And lift is the upward force that an airfoil creates. Drag is the force produced opposing the movement of the blade, similar to friction. And CL and CD are coefficients of lift and drag. And CL and CD depend on the shape of the airfoil, and these are used to calculate lift and drag. Now, lift and drag ratio, or CL over CD, is a measure of the efficiency of the airfoil. The higher the lift to drag ratio, more efficient the airfoil will be. Now, the angle of attack, or alpha, is this angle shown in the diagram below. It's between the incoming airstream and the front tip and the back tip of the air. Now, the methodology for my project. And first, we will obtain and graph a baseline performance measurement of the Mars helicopter airfoil using a software called Xfoil, which is an interactive program for the design and analysis of airfoils. And then I will select a sample of existing airfoil designs from published literature and use Xfoil to analyze the performance under Mars's atmospheric conditions. Third, I will compare the performances of these airfoils to that of the Mars helicopter airfoil and determine the best design option and make any necessary design modifications. And finally, for the best airfoil design, I will translate its efficiency gains over the Mars helicopter into performance improvements in range or payload or flight time. Now, there are some special considerations that need to be made when we're flying on Mars, and that is the gravity is different, the atmosphere is different, and speed of sound is different. Gravity is important because less gravity means less force upward needed to fly, and Mars has less than half the gravity of that of Earth's. Atmospheric density on Mars is around 100 times less than that of Earth's, which makes creating a lot lower lift very hard, which is why the RPM is so high at 2,400. And the speed of sound, while it may not sound important, is actually pretty important because on Mars, the speed of sound is much lower. And what the problem that creates is that with low speed of sound, fast rotating objects, fast moving objects can get near the speed of sound. And if they do, they will start to create shock waves, which will mess with the physics of the object. And in the case of a blade, it will prevent it from making the lift that you want it to. Now, selection and comparison among three airfoils. Before we get into the other three airfoils, let's first talk about the baseline performance of the CLF 5065, which is the Mars helicopter airfoil. As you can see here, this is lift compared to efficiency. Near higher lift values, your efficiency for the CLF 5065 is very high. And for lift, it has decently high lift compared to the rest of the airfoils. Nothing special. And for the rest of the three airfoils, they are Epler 61, which is in green, AS6091, which is in yellow, and AS6092, which is in purple. And these were evaluated using exfil under these Martian conditions, and they were compared against the CLF 5065 airfoil in these two graphs. And AS6091 is the airfoil that I chose to continue on with because it's the most efficient, as shown on the right. It has the highest CL over CD, and it doesn't lose that much lift for its efficiency. It's in the middle of the pack. It's with the rest of the airfoils in lift. Now, editing the chosen airfoil. So the problem with the initial AS6091 airfoil design in yellow is that the back end or the trailing half of the airfoil is extremely thin, and this is really weak and it can break very easily, and that's bad. So we increase the trailing edge gap to 1.5%, so it won't break as easily and hopefully will perform well. Changing the trailing edge gap will also change the aerodynamic properties of the airfoil. So this is why I replotted in comparison to the AS6091 before the change and the Mars helicopter airfoil. Red. Now the edited version actually creates more lift and is more efficient for higher lift values or CL values. And this actually is beneficial because Ingenuity, as you will see on the next slide, will hover at pretty high CL values. And the limitation, as I just said, is that Ingenuity hovers at its max efficiency at 0.722 CL, which is what the CLF 5065 hovers at. The problem with this is that our edited new airfoil, its max efficiency is farther back at 0.65 CL. But what I can do is that I don't need to change the airfoil's dimensions or its shape. Instead, I'll increase the blade itself. I'll increase its width by 10%. And this actually creates a little bit more drag, but it also evens out in terms of the liftover drag for higher CL values. And on the new graph, we have something else called lift newtons on the bottom. This is just lift in newtons. And as you can see, the peaks of efficiency are lined up, which is what we want. And this actually causes 6% less drag with the new edited airfoil because it has more efficiency at the hovering point. And this causes 6% farther range and flight time, or it can carry an extra 0.1 kilograms and still perform as well as the original Ingenuity before any changes. Now, the conclusion of my project, and that is, it is possible to improve Ingenuity's efficiency under the Martian conditions. And by selecting AS6091 and editing it as so by changing the trailing edge gap, the resulting airfoil is more efficient. And furthermore, by increasing the blade size by 1.1 times, specifically width, we can produce 6% less drag when hovering, which leads to 6% longer flight time and an extra payload of 0.1 kilograms, which could translate to some more scientific instruments or other things like more battery or power. And that is it for my project. And thank you for viewing my presentation.